Tonight, in a special program, the Sky at Night takes to the air in a converted jumbo jet. On board is one of the most amazing telescopes ever built, and we're going to see it in action. So welcome to the Sky at Night at 40,000 feet. We're on our way to NASA's Armstrong Flight Research Center, a couple of hours' drive from Los Angeles, because tonight we're flying with SOFIA, the world's only airborne observatory. It may look like an ordinary Boeing 747, but this ex-passenger aircraft has been specially converted to carry a 17-ton telescope that sees the universe not in visible light, but in the infrared part of the spectrum. Visible light, the light that we can see with our eyes, only reveals part of the universe around us. In fact, over half the radiated light comes in the form of infrared, which tells us about the formation of galaxies, of stars and of planets, and even of black holes. It tells us the secrets of our cosmic origins. You can record infrared light with a thermal camera like this one, or with the vastly more sophisticated SOFIA, the Stratospheric Observatory for Infrared Astronomy. Before we took off, I caught up with the man who pioneered the observation of infrared radiation from the center of our Milky Way galaxy, way back in 1966. He could also be said to be the father of SOFIA, Eric Becklin. So we're here with this noisy aircraft behind us because we want to fly in it to go and look at the infrared. But what is the infrared?
The infrared is the wavelengths of light that are beyond the red. It's a very important extension of the optical spectrum, and it's basically heat waves. So we are detecting heat waves out in space.
So why do we need a plane to get to these wavelengths?
Because it's like it's cloudy all the time down here on Earth in the infrared. So we want to get up into the stratosphere. You get into the stratosphere, above most of the water vapor, and it clears up, especially out into what we call the mid and far infrared, where most of the radiation from our galaxy and other galaxies is coming out.
I want to imagine what it would be like to be able to see the far infrared with my eyes. So let's pick something familiar. Let's say I look towards the constellation of Orion, but in the far infrared. What would I see?
The picture you get of what's out there in a region like Orion, where stars are forming, is completely different when you look in the infrared. There are some things that are completely invisible that you only see in the infrared. There's a bar of emission you see in the optical, but in the infrared it comes out really bright.
And one of the things that you see in the infrared is something called the BN object. You discovered that when you were a graduate student.
That's right.
And that's the brightest source there.
That is no, it is not the brightest, actually. There are some things that are brighter, but it was the first one found. They're believed to be forming stars, and they're in the youngest stages of formation. So this is that closest region where massive stars are forming. The BN, or Becklin-Neugebauer object, is 1,400 light-years away in the Orion Nebula. It was discovered by Eric in 1967, the first protostar ever seen. And since the launch of SOFIA in 2010, Eric and his team have been able to explore the infrared universe in even more detail. You've looked, I know, at the center of our galaxy, at the center of the Milky Way, where there's this supermassive black hole. What does the infrared tell us about the galactic center? Well, first of all, the infrared is what allowed us to see that there was a black hole there, because there's so much dust between us and the galactic center, the light is completely extinguished by a factor of 1 billion.
Wow, so you can't see anything.
You don't see anything.
Yeah.
So you have to go into the infrared, and you can see through the dust, just like you can a fire when it's smoky. They have infrared view cameras, see right down to the fire. We do the same to the galactic center. So that's how we actually saw there was a black hole. But now, in addition to that, with SOFIA and the mid and far infrared, we can actually see the dust orbiting around the black hole. So it's very much like the fact that planets orbit around the sun.
Yeah.
But now we're talking about material and stars orbiting around the black hole.
Well, it's a pleasure to be here. I'm looking forward to getting on board. Thank you very much.
Have a good
and
flight.
Thank you for SOFIA.
I mean, I hope you enjoy it.
Yeah, I'm sure I will. Thanks.
Yeah.
Back on board, the mission is about to get underway. Ready for takeoff, and for the next 10 hours we're travelling to the cutting edge of infrared astronomy. We'll be finding out how this magnificent, slightly odd machine operates and why it's so important for astronomers to view the universe with infrared eyes. By climbing 40,000 feet into the stratosphere, SOFIA rises above 99% of our infrared blocking atmosphere. And now we're up here, the first job is to uncover the telescope and calibrate the instruments. So, where are we? What are we looking at?
Well, Chris, we're about an hour and a half into the flight, and we're looking at Mars. It's a calibration leg.
Okay, that's what we can see on these screens here.
Yes, the screens here are showing our 3 guide cameras, and there you can see Mars in all 3.
Training the telescope on an object of known brightness, like Mars, lets the team calibrate the instruments and tune out the background noise.
It's a standard technique to remove the background in the infrared. Now, in the visible, this is not an issue. You don't need to do this.
The sky is dark.
The sky is dark, but at our far infrared wavelengths that SOFIA is designed for and our instrument is sensitive to, you need to remove the background. And Mars, very interesting scientifically, is also a great calibrator.
So for now, we don't really care about Mars. It's just a standard light in the sky.
Yeah, it's our standard star, but we're using the planet.
We rushed to get here.
Yeah, we had this particular flight, we had a narrow takeoff window of about 14 minutes to catch Mars when Mars was at an elevation viewable.
There's something brilliant about rushing to take off in a plane because Mars is setting. I just think there's something wonderfully poetic about that.
Yes.
For the first 2 decades of its life, SOFIA was a passenger jet. But it was acquired by NASA in 1997 and extensively modified. Where once rows of passengers sat, now a 17-ton, 2.7-metre reflecting telescope resides. To limit the impact of having a huge open door in flight, the fuselage was also modified to avoid turbulence. As the science team settle into their 10-hour flight, pilot Dean Neely has time to take a break from the cockpit and tell me what it's like to fly. So, how's your evening going?
It's great. This flight's gone really well. A lot of work from a lot of people leading up to it really made this happen, so made it fairly easy and smooth to execute.
And so how does flying a plane like this compare to a normal aircraft?
It's very unique for several reasons. One, it's huge, as you can see. One thing that reminded me as we started the engines began to taxi out tonight, I always feel like I'm driving a stadium around. You know, you're so high in the air, and steering this thing is unlike anything else. So it's a very large aircraft. And then you take on top of that the special design and the modifications, putting this incredible telescope in the back. I mean, there's nothing like it anywhere in the world.
Because of those modifications, if you took, say, a commercial pilot who'd spent their life flying 747s, and you put them here and you didn't tell them about the back end, do you think they'd notice just from the way it handles?
Honestly, no, they wouldn't. Because of the amazing way that they did the aerodynamic modeling and designing with the structure in the back for the telescope assembly. In fact, when the whole back side of the aircraft opens up for the telescope to look out, in the front, I would never even know it, except there's a little light on a panel that says it's opened or closed.
So, in preparing for an evening like tonight, how much back and forth is there with the science team? How much negotiation about what's possible and what the ideal situation would be?
What you see going on here is only a small part of it. So the planning for this started many months ago. The astronomers and the science planners putting together a rough plan, and then they pass that to an aircraft planner, typically as somebody who's a former navigator who understands the flying. So as you lead up to the day of the flight, they go a few rounds starting 36 hours prior to the flight, and then the last round to finalize the details of the timing and everything is 12 hours prior to the flight.
What about when we're flying along? We're at 43,000 feet right now in the middle of an observation. Are you having to do things to try and keep the flight as steady as possible, or does the telescope take care of that for you?
No, the telescope does most of the precise hard work, and what we've got to do is just keep the aircraft as steady as possible, because it's very sensitive. So when we make turns, we make very small turns, 1 degree at a time, maybe 1 degree every 20 or 30 minutes typically. And we make sure when we do those turns, we only use 1 or 2 degrees of bank. We have to think ahead because we can't just maneuver like a normal aircraft would, including climbs and descents to different altitudes, things like that.
Yeah, I noticed this evening there's some negotiation, or at least chatter amongst the team about when to climb and how fast to climb and so on. It seems collaborative.
Yes, very much so. The people driving the airplane up in the front have to work through the mission director, who is kind of like the orchestra conductor, working with everybody else down here, including the telescope operator. The one thing you have to get used to as a NASA research pilot is when you get in a group like this, I have to be humble enough to understand that I'm the dumbest guy in the room and just drive the plane the way I'm supposed to.
Rather important, though. So we should let you get back to it. Thanks for your time, and enjoy the rest of the flight.
Sure, it was great talking with you.
Thanks.
SOFIA's focus is the far infrared, which makes it ideal for astronomers who want to peer through gas and dust. One of the biggest mysteries in astronomy today is how dense clumps of gas form into stars. SOFIA's high-resolution Airborne Wideband Camera Plus, or HAWK Plus, is used to investigate just that. I caught up with project scientist Kimberly Ennico-Smith on the much quieter upper deck.
So, one of the reasons we're here on this marvellous aircraft is to learn about star formation. What do we know, and what are the mysteries of star formation?
Big questions, Chris, and questions that we've been asking for a long time and learning as we go. But if you think about it, some of the big questions about stars and how they formed are still unanswered. There's a mystery out there. Why, when we look at our Milky Way or we look at other galaxies, why are stars forming in certain regions and stars are not forming in other regions? What makes those places special? What makes them different?
And it's infrared that matters because that's where the action is.
These wavelengths of light longer than our eyes can see allows us to peer deep into clouds that we wouldn't see in the visible. And that means we could get at the heart of, where stars are forming. A lot of the images that we're taking in the infrared don't show the stars at all. They're showing the dust from which stars are forming or into which stars are going after they had at the end of their lives. So the study of dust is equally important to the study of stars.
What does HAWK actually see?
HAWK's an infrared camera, so it's taking pictures, and it works the far infrared, and we're looking at the far infrared, and so we're going to be measuring cold things as dust being emitted, cold dust.
I know there are results already, so can you say something about what HAWK's found so far?
Yeah, so it's not published yet, but we
Even better.
I know, but it's just really exciting. So one of the new developments in star formation theory is the observations that there are these structures called filaments.
So we've got some images here. So this is optical, I
That's in the
guess.
optical, and you see this filament? It's this long, string-like, snake-like cloud. They could be several degrees on the night sky. And in the longer wavelengths here, you're seeing the gas along the filaments glowing, the re-emitting of the
It's
light.
the opposite, right? In the optical, the filament's dark.
Dark.
But here, it's the thing that's glowing brightly.
And then you see the hot spots?
Oh,
These
yeah,
eyes?
yeah.
Those were stars forming, or are they just formed? When Herschel did this all-sky survey and found these filaments were everywhere in the Milky Way, some of the filaments have stars and some of them don't. So there's a mystery. We're thinking this is how stars are forming along these filaments, but what can create the stars from forming? What might stop them? Might speed them up? A lot of mysteries.
So stars are forming these filaments, but it's not that the whole filament suddenly lights up. Bits of the filament.
No, little bits, but sort of like on your Christmas tree with your fairy lights, right? It's fairy lights on your tree.
By looking at the light from the filaments in detail, HAWK Plus can detect magnetic fields within them, perhaps a clue to how and why the stars are forming.
So what's interesting with the new data from HAWK Plus on SOFIA is measuring the magnetic fields on filament scales, actually looking at the shape, the orientation of the field, and we're finding they're perpendicular to the direction of the filament.
So the filament goes across like this,
Yeah.
then
And
the
magnetic
field
field is going
comes
like
down.
that. Or like this. It's
And material would tend to
orientation.
flow along the magnetic fields, presumably, possibly.
One could guess. Or it could be a barrier. It's unclear. So one idea is just like, a hedgerow on the countryside, and it's a windy day, and you have, this time of year, we have lots of leaves falling down.
Yeah.
If you have that wind blowing perpendicular to the hedgerow,
Yeah.
the leaves start accumulating.
Huh.
Could the magnetic fields, if they're perpendicular to the flow, be a channel to, add material or create instabilities for which chaotically things will collapse and form
So
stars?
those are then the places where stars will form.
Could be.
And the critical thing here is that the instrument, HAWK Plus, allows you to look at what's going on in the filament. Previously, we've only had a really broad brush look.
That's right. Now we can zoom in and see where the action is happening.
Well, it's clear we're just at the beginning of what HAWK Plus will do, so I'm looking forward to seeing the rest. Thank you very much.
Thank you very much, and it's a pleasure to host BBC Sky at Night
Thank you.
on the world's premier flying observatory.
We're well into the flight now. We're about 1,000 miles off the coast of California. The telescope is looking at its science targets. The plane's moving around a bit, even though we're up at 40,000 feet, which begs the question, why would you put a telescope on a vibrating platform like an aeroplane at all?
Making sure SOFIA's telescope stays trained on its targets is Emily Bevins.
So you're one of the telescope operators, which is an important position in any observatory.
Right.
So what is the telescope operator?
What we do as telescope operators is we control the actual telescope and movement to make sure we're pointing and collecting the data that we think we're collecting. It's a very narrow beam of light that you're trying to track onto. And so you're just making sure that your telescope that you're using is collecting these really narrow beams of photons that we're getting from space. And so it's like a tightrope walk almost.
I was going to ask, with the movement, standing at the back, watching the telescope wobble around, that seems like that would be problematic.
Yeah, SOFIA is kind of an interesting telescope because it is on the back of an airplane. And that does change things up quite a bit from being on the ground. And so not only are we concerned with tracking, but we're also concerned with the movements of the plane. Or if you have a ground-based telescope, you're not as concerned because it's not always moving. It's not changing direction.
How does the telescope stabilize itself?
And it has a series of pneumatic tires around it that kind of keep it pressurized, but we also have a lot of gyroscopes attached to it that keep it stable as well, which is really important for what we're doing here as telescope operators. So when you do see the telescope moving around, you want to panic. But everything's stable. It's a really well-engineered telescope. And so you're not actually watching the telescope move, it's you that's moving.
It's pretty cold in here. Why don't you have heating in here?
Very cold in here because we want to keep the temperature pretty equal to what the instrument is going to be at. So we're actually in the same room as the instrument.
With SOFIA, of course, we use many different instruments. Can you tell us how that works?
Yeah, so we do a bunch of different instrument swaps, and it actually keeps it pretty exciting because you always have a new instrument every couple of weeks. So within the past month and a half, we've done 3 different instruments.
And when I look down towards the telescope end of things here, how much of what I'm seeing swaps out?
The majority of what you're seeing with the telescope stays there. It's only like the back portion of it that comes off. And so each instrument's kind of different sizes, but they're all still pretty compact because we still have to get them through the plane door. It's really important to be able to switch them out back and forth so quickly. It gives us a lot of access to a lot of science, a lot of different types of science, and it's a kind of a really special part about what SOFIA is able to do up here.
Well, you could never do that with a space telescope. It's much easier with an aircraft than a satellite
It
to
is,
do that.
yeah, absolutely.
Tonight, the team are using the telescope to investigate how stars evolve. But the ability to continually swap out and customize different instruments for different tasks means that SOFIA has been able to investigate many different phenomena, from dust circling around black holes to the activity of passing comets. And it will soon have another string to its bow. It will be able to probe how planets form. Because NASA's currently building the next generation instrument, the High-Resolution Mid-Infrared Spectrometer, or HERMES. Before taking off, I met with Sam Richards, who's one of the team designing and building the instrument.
So Sam, thanks for talking to us. You're working on the next generation of instrument for SOFIA, something called HERMES. What is HERMES and what is it going to do?
HERMES is looking primarily at protoplanetary disks. And these are disks around other stars where once a long time ago in our solar system, it was just a disk of material, dust and ice.
This is the leftovers from star formation.
Exactly, yeah. So it accumulates around in a disk around the star, and then those disks, the particles can join together and they build up, small little pebbles, and then the pebbles become rocks, and the rocks become asteroids and comets and things like this. And eventually you get planets.
It's always amazed me that we don't really understand that process, how the dust sticks together.
Exactly, yeah. So we have our own solar system, which is one data point, and we know it fairly well, but we still don't know why it's in the order that it is and where all this material and chemicals came from. So this is one of the key reasons why HERMES is being made. With the high resolution aspect of it, we can understand how this material is moving around other stars, and then how the different components like the water and the ice and the oxygen and all these kind of key life-building components, how they come together and then they evolve over time to eventually create what would be a solar system like the Earth, and with gas giants like Jupiters and Saturns and things like this.
Why is it important to look at the water and the oxygen? What stories do those tell us?
One of the big questions about how Earth got its water and why it has so much water is, how did we get here? Where did it come from?
We think the early Earth was dry,
exactly.
Right? It lost all its water, and we've got to get it back somehow.
And we need the high resolution science to be able to figure out exactly kind of how all this chemistry moves around in the disk.
Yeah, so that's the point, isn't it? It's telling you what's happened to this material over time.
We're on this long journey to figure out where our solar system fits into the story of all the other potential solar systems out there, and then we can figure out which family tree that we came from, and then kind of backdate the models that way. So
this is exciting stuff, and this will depend on HERMES, which I think will start flying, next year, something like that?
So HERMES is currently in the kind of building phase, so we're currently putting the components together, and to achieve this type of science, you really need a high level of complexity, which you can't really do from space, and SOFIA is the perfect platform for this type of instrument.
You're fairly new to the project, I think. Yeah. Have you flown on SOFIA?
Yeah,
so what was your first flight like?
I'm a total fanboy, so when it comes to NASA and this type of mission, you get to don the flight suit, all the patches, and you're really going to get to enjoy being in the moment there. And something that's very different to kind of ground-based observatories.
Well, good luck. I hope all goes well, and I look forward to seeing the results from HERMES. It's really exciting.
Yes, thank you. We're excited too.
It is going about the details of how stars actually form. And not only that, but once when they burn, they give radiation back into what we call the interstellar medium. And to study those details, we all know these iconic pictures of the Hubble Space Telescope, the pillars of creation.
That's right, yeah, which is the place where stars are forming.
Where stars are born. But the thing is, in those optical pictures, you cannot actually see the creation, because that is inside those dark gas and dust clouds. So the optical radiation doesn't penetrate that dust.
One of the main missions for GREAT is to understand the early stages of stars' lives and star formation. How do we do that using an instrument like this?
With the molecular radio radiation that comes out of these dark clouds, we can actually probe the details of the physics happening there. So the motions of the gas, temperature of the gas, for example, collapsing motions.
So you can actually see, you can look at it, what in an image would just be a blob. Because you're looking at how things are moving, you could say this is collapsing, this might well form a star.
That is one of the data that we get out of those spectra, because we see the motions of everything and really the physics, not just the optical radiation or the pretty pictures, but really the detailed physics of what is happening in there.
So if you look with this instrument at a newly forming star, right at the beginning of the process, what do we see?
We actually can see the collapsing motion of a molecular cloud that leads to the formation of a star.
So you could point and say, we now know, thanks to Grace, that cloud might form a star.
Yes, that is absolutely right.
It would be good to know a bit about the objects or the observations that are being done specifically on this flight.
One interesting goal, for example, was there was one source where people had an idea, a model, how the movements of that source were. And so they saw a double-peaked structure in the spectral lines, which they interpreted as being two different speed components.
With some of the gas going in one direction or at one speed and some going in a different speed.
I hope I don't tell too much of the secrets here.
Well, you haven't told me which source, so I think we're probably okay.
But in this 3/4 of an hour that we observed that source, we shattered that theory.
Oh, wow,
So
okay.
it's not true. It's not two components.
So this is something you didn't know a few hours ago.
Exactly. So that's a new thing.
It's kind of amazing to think that we're sort of seeing what our sun was doing 5 billion years ago.
Yes, of course we cannot really observe the complete formation, but we can observe different sources which are in different stages of star formation. So that is how we learn how that finally works. Because we cannot, of course, stare at it for 250,000 years.
Yeah, and one of the most amazing things about star formation for me is that we've known the basics for a long while, but the details are still very obscure. We don't understand them.
That is absolutely right. So that is what we are looking for, and finding new things every day.
By expanding our view into the infrared, SOFIA shows us snapshots of stars and planetary systems of all ages. And put together, these snapshots help tell the story of our own solar system and build a clearer picture of the universe.
It's about 3:30 in the morning. We've just landed. I'm pretty tired, and so are the crew. It'll take them weeks and months to analyse all the data that they got just from this evening's flight. One thing's for sure, though, this is a marvellous way to fly and see the universe. When we come back next month, we'll be on the edge of the solar system. Until then, good night.
Chris Packham and Michaela Strachan go in search of northern lights and the Star of Bethlehem under a Christmas sky on the 23rd of December, BBC 2 at 9. And the Sky at Night Book of the Moon is now available.